Okay, so before we go to thermal comfort related equations, we will look into a little bit into heat flow path in buildings, but then we will go back a little bit more related to conduction we will look into, so that it will become easier to understand the thermal comfort issues, because the comfort equations should come. So we will look into this. Now if you look at the building, right, if you look at the building, various heat flow paths, this is basically, there would be direct sunlight can come like this, direct sunlight can come like this, solar radiation, solar radiation can come like this, and if you have a window, then the direct solar radiation will be received in this manner. But solar radiation can fall also onto opaque bodies like your roof, wall, etc., and this will heat up this surface itself, and then it will transfer by conduction. Temperature here would result in heat conduction, which could be both ways, coming in or going out, right. So heat conduction, heat gain can occur through the wall. Some emission, radiation in the night, the surfaces can radiate back to the atmosphere, right. So conduction can be both coming in or going out, and through openings ventilation heat transfer can occur, which can come in or get out, or whichever way out. In addition to that, you will have some heat generation from human bodies, appliances, heaters, etc., etc. This is a situation where you have actually your cooling situation. So you have put in a heater. If you have fan, that will also generate. So these are the so you have direct solar radiation, and if I make it a little bit more, something like this. So solar radiation coming like this. This is the window. So through the window there will be a little bit of conduction also, but if there is a glasses, through that there will be conduction also, and some heat gain from the body, human body, we call it casual heat gain. Conduction through the solid wall could go in or outside. Conduction through the roof can also occur, and conduction through the floor, etc. So this gives you a kind of basic idea about the modes of heat transfer. So you have conduction, essentially direct radiation can come in through the opening or glasses, which allow transmission of radiation. So direct radiation can come in. Conduction heat transfer takes place through the opaque bodies, like wall. If the outside temperature is high, heat will come in. If the outside temperature is low, it will go out. Direct radiation which falls onto the opaque body, finally they are transferred inside by conduction again, because they will heat up the surface or the wall, etc., and it will allow. So conduction heat transfer, direct solar radiation we have looked into. Ventilation heat transfer can take place if I have openings, right, and from wall to inside, again it will be through surface coefficients or whatever it is. So this diagram shows you the modes of heat transfer in building, modes of heat transfer in a building or in a space within building, as we have seen, right. And if I can make it fairly complicated by this kind of a diagram, but its simpler one is already there. There will be like for example, this is external convection, this external long wave radiation. Now I might have mentioned to you what is long wave radiation or short wave radiation one day, but I will explain it again. Other day when I was talking about the glass, properties of glass, or I was talking about Earth's heat balance. That time I was telling you that whatever heat annually comes in, it goes out, but if there is a carbon dioxide cover, it can actually block some of the heat going out, like glass, like greenhouse gas we are talking about, or greenhouses we talk about. So glass has this property. You see, the quality of radiation or characteristics of the radiation depends upon temperature of the body. Sun radiates at very high temperature, right. Therefore, it radiates spectrum of radiation, which includes visible, ultraviolet, visible, etc., to infrared heat radiation as well, right, because it radiates at very high temperature. While you come to terrestrial bodies, Earth, it radiates actually at much lower temperature to the outside cosmos, which is at lower, still lower temperature. In the night, the Earth will radiate back. Now, since its temperature is low, it can only radiate long wave radiation, or it is a function of temperature. It's law of physics, actually it's a function of temperature, the lambda value. So, it is usually long wave radiation, low energy radiation that goes in. Now, this radiation are, they are not capable of getting transmitted through glass. So, glass traps the long wave radiation, but allows short wave radiation to come in, right, allows short wave radiation to come in. So, building will actually radiate only long wave radiation back, building will radiate long wave radiation back. So, therefore, external convection and long wave radiation. So, from the surface, but all radiation outwards from the building or earth will be all long wave radiations, right. So, in fact, just we will discuss this sometime later on. That means, if I look at the absorptivity of a absorptivity of a surface, I should have, let us say, opaque surface, whitewashed surface, is absorptivity to solar radiation should be low, it should absorb least, right. Absorptivity is a fraction of energy it absorbs, but its emissivity to long wave radiation should be high, so that it absorbs least, but in the night it radiates out maximum. So, this character is a long wave, it is all long wave. Similarly, it is shown here, transparent surface solar radiation gain. So, more complicated, this is the air node inside. So, from wall to inside there will be convective heat transfer and radiative heat transfer. But what we do is we simplify many of them. So, one can make it relatively complex as this diagram shows, but we can still make it far more simpler, we will see that. So, if I write the heat conduction into the building is transient conduction, because temperature outside is varying. Transient is what? Non-steady state. What is, okay, I think I may not have defined this. Steady state is temperature remaining constant, which will never be the case. Over a short range you might approximate it in certain climate, the temperature outside remains constant, but reality it will never be. So, temperature will have some kind of variation, and therefore, it is not, it is non-steady. Transient or dynamic is also used synonymously with non-steady, but transit, it can non-steady state also can be of varieties of kind, or transient can be of varieties of kind. For example, you can have sudden increase, right, and then come back, transitory or periodic and so on. So, anyway, so this is conduction through opaque bodies, surface convection and intersurface, surface convection from surface to inside, then intersurface long wave radiation between two surfaces, external surface long wave radiation going out, that diagram that was there, that included all of them, short wave radiation coming inside the building through the glasses. If I have a shading, they can actually block that, and insulation actually it is, anyway, infiltration and natural ventilation. So, air movement can, hot air from outside can bring in heat, or if I have hot air going outside from inside to the room, it will take out the heat. Cool air coming in winter, cool air coming from outside makes it cool, right. And if cool, like basically room is maintained warm, therefore, cool air you do not want it to come in winter, but summer you would like, if the outside air is cool, you would like it to come. So, these are related to natural ventilation, and infiltration I said was unwanted, forcefully entering. So, if you have leakages at the window, door, construction defects which allows air movement to take place, that is what we call it infiltration. Casual gain from human body, appliances, etc., that is what we call as casual gain. So, if I summarize them, conduction through opaque surfaces may include effect of radiation falling onto those surfaces, because opaque surface will get heated up, and direct radiation to transparent surfaces, glasses, transparent surfaces, and heat exchange due to ventilation or infiltration, casual gain. So, all these diagrams that are far complicated, finally I might summarize them into these four for our purpose. So, basically conduction through opaque bodies, walls, ceiling, roof, whatever they are, and if radiation is falling onto those opaque body, finally they will be transferred inside through conduction only, and then direct radiation through glasses, heat exchange due to ventilation and infiltration, if there is a air flow through leakages that will bring in heat or take out heat or whatever it is, and casual heat gain from human bodies, appliances, etc., etc. So, when we can model them simplified form, we are trying to keep it simple as much as possible for amenable to hand calculation. Computational program can be very robust depending upon what one is doing. There are softwares available, as I mentioned, but to understand this, these are the summarized, these are the mechanisms of heat transfer. So, we define something called thermal transmittance, right. Well, we said that building is supposed to act as a filter. Sometime I think in the beginning I mentioned that it allows good thing to come in, it is a moderator, do not allow bad thing to come in, that means it will block the summer heat, allow winter heat to come in, summer block the summer heat, but required light all the time for internal. So, wall being a part of envelope plays a key role. So, wall and roof, they play very key role actually, as because envelope, part of the envelope, right. So, they are they are the major moderators, which envelope is a major moderators. So, wall is one of the main thing. So, we will look into some of those words. Now, this, as I said, that heat flow, conduction heat transfer here is transient or dynamic. Now, situation here is actually when you are looking at dynamic situation, we can do one thing, we will discuss this in details later on. Supposing this is 8 am today and 8 am next day, and let me say I have some temperature, this axis is temperature, right. So, what you will find is if I have a temperature, let us say some temperature, let us say something like 37 or 25 degrees somewhere here, then it will go on increasing and possibly next day also it will be somewhat similar, and again it will be somewhat it might be something like this, similar, some sort of, you might find something of this kind. Usually temperature is periodic, 24-hourly periodic, because it is related to sun's rotation. I am just talking of external temperature. So, when I am talking of dynamic here, I am looking at a situation of periodic heat flow. I am looking at the situation of periodic heat flow, right. When I am talking of dynamic, in case of heat transfer from surrounding to the building, I am looking at this situation. That is what is been stated here. So, periodic, here it is dynamic heat flow. Dynamic heat flow is periodic actually, because I can assume that 24-hourly period and everything will be periodic as long as my season is same. Over a period of time, over a given season, even in composite monsoon climate which has got 3 different seasons, you might assume that it is by and large periodic for certain period of time. So, that is how it is. Okay. So, let us look at this part, but steady heat flow is important. Why? Because I can find out the mean of this heat flow, and today's mean and tomorrow's mean will be same, outside mean will be same. So, I can assume that remains constant, mean remains constant. Now, this is outside mean. Now, inside mean also will remain constant, because whatever sometime it will be absorbing heat and sometime it will be giving away the heat, right. Otherwise, its temperature will go on building up. That is not that cannot happen, because outside condition is by and large same periodicity is maintained. If I assume that they are all periodic, similar, what we call steady periodic situation. Steady periodic situation. Steady periodic means it's periodic, but remains steady. Now, that would be over a season, by and large it will remain steady periodic. During the transition from one season to another, of course, there will be changes, even internal temperature would change. So, coming back to this, so this might be my outside mean. Inside mean could be somewhere else. Well, for the time being, let me put it, it might be somewhat higher, let us say, or higher or lower, that we will see later on. But that will also remain constant. Today, tomorrow it will remain constant, because there also it is periodic, inside also will be periodic. I am not talking of conditioned building, unconditioned building, because it will receive some heat and give away some heat. So, inside condition also would be periodic, and that is our common day experience also. Sometime in the day room is very warm, and sometime in the night it is not so warm, So, there is a change and it is periodic again, 24 hourly periodic we can assume. So, if I deal only with the mean and deal with this fluctuation separately, this fluctuation from the mean separately, some fluctuation will be plus, some will be minus, right, and sum up their effect together, then I can get the overall effect, right. I can superimpose the effect of the means and effect of the variation from the mean separately and add them up. You can add them up as long as your phenomena is or equations are all linear. In a linear system, f x plus 1 x 2 is equals to, or k x 1 k 1 x 1 k 2 is equals to f of k x 1 plus k 2 f x 2. Independently you can sum them up, these are constants, and you get the same thing. You can understand that many of the structural engineering scenario you do that. P1 force, effect of force P1, you can add the effect of force P2. Supposing you want to find out various effects like deformation related to a force, you can sum it up as long as the system is linear, right. But if your modulus of elasticity is varying with it is not linear stress strain diagram, then you can't do this, there will be problem, because you can't add this effects. So, as long as linear I can do this, and we assume here heat transfer situation is linear heat transfer situation. So, therefore, there is no problem, we can sum up. It is very simple algebra, nothing like this. Supposing I have got k 1, it is a function of k 1 x 1, but if it is x square, x 1 square plus x 1 plus x 2 square, x 2 square is not equals to x 1 square plus x 2 square. No, whereas if it is linear, then x 1. So, that is basically that's the idea, you can see that. We separate out the steady part and non-steady part. Let us look at the steady part right now. That is why I was just telling you all that. So, let us come to the steady part now and define that transmittance that I was just mentioning. So, steady heat flow through a wall, let us look into. So, I have a surface, let us say surface temperature is T2 here, and that side it is T1, and these sides are all insulated. These sides are all insulated like a brickwork or very large, this side is very large, infinite such compared to this thickness. So, that we can assume the heat transfer is occurring only in one direction. We are not very close to the edge of the wall. So, we can assume heat transfer is only one dimension. This area meter square, this surface temperature is T1, this side is T2, and from my heat flow then would be total heat flow will be given by heat flow per unit area was small q, which was k T2 minus T1 by L. Remember we said q is equals to k dt dx, and I can write it as k T2 minus T1 divided by L, if L is the thickness. So, that is what I am doing, multiplying by the area will be capital Q. So, capital Q will be capital Q quantity of heat flow watt per meter square, rate of heat flow is K A T2 minus T1 divided by L. K is the thermal conductivity, right. This degree is not there. what the K I think is not written with degree, it does not matter. Now, supposing I have a layered situation, then heat, and now my temperatures are all constant, because I said that I am looking at the steady scenario, right, steady scenario. So, let us say I have one layer whose conductivity is K1, thickness is L1, second layer conductivity is K2, thickness is L2, and so on Tn. Heat coming here is Q, heat going out also should be Q, because it is steady state. So, heat passing through each one of them is same. So, Q will be equals to K1, this K1 into A into T1 minus T2, divided by L1, and this heat is coming to the next layer. So, I can write for the next layer K2 A, area is same, etc., and I can do this for all. And then I just separate out T1 minus T2, I can write T1 minus T2 will be equals to Q by K1 A. Similarly, I can write, and where is L gone? L will be together here, right? L will be here only, L1. Similarly, T2 minus T3 will be written as Q L2 by K2 into A, right, and T3 minus, I can go on writing like this, corresponding one. And if I sum up this T1 T2, T1 minus T2 plus T2 minus T3, etc., what you will find that these two will cancel out, T3 will also cancel out, I will be only left with T1 and Tn. And this algebra I am just doing this, I am just doing this algebra now. So, T1 minus T2 plus T2 minus T3, etc., will be Q by A will be common, because Q by A, everywhere Q by K. So, I will be left with L1 by K1 plus L2 by K2, etc., this, right, I will be left with this. Okay. So, this term, when I have layers in series, in if we look at electrical analogy, when resistances are in series, you add up the resistance, and resistance is nothing but resistivity and resistance. Resistance is rho L over A, resistivity is rho, resistance is rho resistivity multiplied by L by A in electrical. Here also similar analogy you can look into, L1 by K1 into A, if I take it, that is basically nothing but the resistance of this unit. I am summing up the resistances actually, when they are in series I am summing up the resistances, alright. So, this actually will cancel out, and I will be left with T1 minus Tn, that is nothing but the potential difference or voltage difference. So, T1 minus Ta is nothing but Q by A into R. So, we are calling this as R of the system, L1 by K1 plus L2 by K2, etc., and R is equals to sum of R1, R2, R3, Rs, that is right. So, when layers are in series, I will have something like this. Layers may include cavity, supposing I have a air gap here, these are all solid, air gap here. So, all I got to do is add the cavity resistance, just add the cavity resistance, or insulation. So, then cavity resistance must be known, and these values are given, I mean people have found out, because internally they will be convective or radiative heat transfer, but then depending upon of course the thickness. If the thickness is very small, generally below 3 millimeter circulation cannot occur. So, in pores really convection do not occur always, fine pores convection will not occur. Even radiation between pores should be very small, because the distances are small, temperature difference may not be large. So, but in walls I will have actually, if I have 5 centimeter 50 mm gap, I will have some resistance, some heat transfer, right, and equivalent resistance one can find out. These values are given in code like SP 41s, Bureau of Indian Standard special publication SP 41, it gives you values of resistances and conductances of many of the material in a gross manner, but it is quite useful for our purpose unless you are looking into more details. So, for values of conductivity, resistivity, conductivity, surface conductance, etc., they are given in many books, but standards they are also given. For example, in Indian Standard special publication SP41 and SP32 they give you. SP41 is for non-industrial buildings. This is this special. I think I have given it in reference, so you can look into SP41. You search the IS Indian Standard Code site, Indian Standard site, you will find it. So they give you those values. So resistances of cavities are available there, right? But there is one more thing remaining. As I said, surface is never solid. Surface is always contact with the fluid. So if outside air temperature is TOA and surface temperature is TO, inside surface temperature is TI of a wall, and inside air temperature is TIA, then there will be heat transfer occurring from this also, because there is a temperature difference. The heat transfer will be occurring from, and heat transfer will occur from this to this as well, right. Now this heat transfer is both by convection and radiation, both free and forced convection, and that H we talked about, it is related to that H. So this heat transfer can be written as this H I, H I I have written, into Ti minus TiA. Similarly here it will be HO TOA minus TO, air temperature minus the surface temperature, where TO is the surface temperature of the wall, Ti is the inside surface. I mean I am writing deliberately inside and outside, so that we get familiar with what actually it is. If so this is the heat. Now what is this? This is the, we call it surface conductance or coefficient of surface heat transfer coefficient, and its unit is watt per meter square, as we have seen already discussed this earlier. So now if I want to find out the resistances of this one, it will be simply 1 over HO. Resistance of this fine layer, air layer, it will be simply 1 over HO, because this is watt per meter square, and temperature difference, because you remember Q is equals to Q was equals to how much was it, K delta T temperature difference, delta T, let me write, divided by L. So L over K is the resistance, L1 over K1, L2 over K2, etc. They were the resistances. Now here Q is a function of H into delta T. So 1 by H is a resistance, H is the surface conductance, 1 by H is a surface resistance, surface resistance, and this has been by linearizing heat transfer and all that we have done, right. So when I take that into account and try to find out the Q again, then I will have H A T O minus this term also I should take into account, and H I, this same heat is passing through this. So I have to take account of that also. So I will have this must be, Q must be equals to 1 by R TO minus TI. This we already have done, last slide we did that, So Q is equals to simply Q by A into R TO, so Q will be equals to Q, capital Q is equals to T1 or TO, in our case it will be TO minus TI into A by R, right. A by R, sorry, A by R. So that is how it is. So I am writing the same thing here, 1 by R into A TO minus TI, and that must be equals to whatever is going out here and whatever is, right. So if I combine this like I did previously, if I combine this as I did previously, I will get 1 by HO, I will get 1 by HO, I will get 1 by HO plus L1 K1 etc., plus 1 by HI, right, because equivalent resistance is this and equivalent resistance is this for the surface layers, and this I call as 1 by U, and this U is called U value, that is a measure of transmittance of the wall, that is a measure of transmittance of the wall, right, that is a measure of transmittance of the wall. Okay. So I think there we are. So we have defined U, and heat transfer, steady heat transfer through the steady heat transfer through the wall will be given as U into A into delta T, where delta T is air temperature outside minus air temperature inside, or air temperature inside minus air temperature outside. So, air to air temperature difference is delta T here into UA, because that is what is known to be me, surface temperature will not be known to me, that is how we define it.